So is there any question now before I start? No? No question? Okay, let's go then. Stresses. The first line is pressure vessels. So you have to be very careful about the new material now. So pressure vessels could be, first of all, cylindrical. So please write it down. Cylindrical pressure vessels. So in that case, it could be open-ended. If there is an open-end pipe or long enough that there is an end to that, will not affect the systems. Generally, when something is very long, but you put a load on it, the load is going to be dissipated after a while, the effect of the load. So you don't have to worry about the length. It's very long. That's the same thing here. So here we have a cylindrical pipe, and then the cylindrical pipe has of course, a very narrow thickness here. So the way it goes, we call this one in the book, we call it R, but be careful here. We have R inside and we have R outside, and the difference between the two is the thickness of the pipe. Is that correct or not? Yeah. Then inside the pipe is pressurized. So when you see this pressure going inside the pipe like this, which is everywhere, by the way, we're calling that one P, which is similar to a compressive stress, which is pressing against the pipe. Is that correct or not? Mm-hmm. However, what happened to the pipe? Is this pipe is going to stretch? I mean, if you have a balloon, you put air in it, as everybody have seen it, it's going to stretch in all directions, yes or no? However, here, because this side is smaller, it's going to be stretching. This pipe wants to get expanded like that. Is that correct or not? Since it's going to be expanded, it's going to be having, if I'm looking at this point here, it's going to have a stresses going like that, because because this is in the form of tension, and we call it this sigma 1. Or Hooke's stress or circumferential stress. Everybody understands the stress is along the circumference of the circle. Is that correct or not? Yes? The question is how much? So if I give you R inside, R outside, and thickness of the pipe, the question is what is sigma 1? That's what the first one we want to find out the stresses along the, which as you look at it, will be like that. Is that correct or not? Yes. If there is a point here, so that point is being under sigma. Correct? Now, to do that, all we have to do, go through a little bit of a static that everybody can do that, is here to take a little strip of this pipe and call it the delta X. That delta X could be 1 inch, half an inch, or whatever. Is that correct or not? And look at that, which I do that, so I see something like this, and with the thickness of the delta X. Is that correct or not? Yes? Then cut this one in half. So when you cut that one in half, this is what you see. So you cut it like that to see this stress is there. Is that correct or not? The stress in the form of tension. Therefore, this is probably what you see. If I can come up with the best picture I can, it's something like that. Oops, not like this. So this goes here, this goes there. That's inside the pipe. Is that correct or not? Yes? And the outside goes like that. And then you see a little bit like that on top. So what are the stresses? What are the sigmas? The sigma is here. And here. Uniformly, we are assuming you are uniformly distributed. Now, why? And that's the question I want to answer. Everybody can see that on the inside the pipe, we have a pressure of P. On the outside of the pipe, we don't have any pressure. Is that correct? It's the air pressure, yes or no? Correct? Therefore, first of all, we have to understand that if this becomes too thick, this formula that I'm giving you is not going to work. First of all, this is thin wall, so please write it down. Thin wall cylindrical pressure vessels. So that means this thickness of T must be relative to the diameter or radius of the pipe must be very small. Is that correct? And the way we check it is like that. The boundary line is that if RO over T is less than 10, then we call it thick wall pressure vessel. If you have a concrete pipe which has a thickness of 10 inch and the radius of 20 inch, that does not qualify for this design. It has to be very thin. Very thin means it's metal, it's a steel. So you have a diameter of 1 meter, thickness of 20 or 25 millimeter. Everybody understand that? So here is the ratio you want to check always at the beginning of the problem. If RO over T is larger than 10, so in other words, if this is 1 inch and this is 12 inch, the ratio is larger than 10. Is that correct or not? Therefore, this will be considered thin wall vessel. And this formula that I will give you in a minute is going to work. Based on that, the stresses being going based because this thickness is very small, the stresses from here to here is assumed to be constant. So it's not changing. Although inside, as you can appreciate, inside you should have more stress than outside because inside the pressure. Because in this analysis, which is very simple, we are assuming the stresses that in this portion of the pipe is all constant, everybody, although there is a slight change there. However, if this thickness becomes much larger, I have to bring that into the picture. Everybody understand that? Then it becomes a thick wall vessel. I have to give you that if you want to, but it's not part of this class. But the formula is half a page for sigma 1 and sigma 2. Everybody understand what I'm saying? So it's not there. So what we are doing here, only designing it based on thin walled vessel. Everybody understand, or we are assuming this is always the case. Is that correct or not? But you can check it for each problem. That's for future reference. Is that correct or not? Yes? So it has to be the thickness much smaller. So based on that, now all I have to do, calculate the forces going in and forces coming out. Everybody knows that sigma times area become force, yes or no? Because force, sigma equal to, after all, P over A. So if I want the forces must be sigma times area. So how much red forces coming out this way, guys? So write it down. I'll have to, in order to calculate. First of all, this is sigma 1. Yes or no? Correct? Sigma 1 distributed over this area. But what is this thickness? That thickness was dx. Is that correct or that's the cut? What is this thickness? That thickness is T. That's the thickness of the pipe. Yes or no? So this distance, in other words, this is T, and that is delta X. Is that correct or not? Yes? So the forces, writing the summation of the forces, going, I don't know what you want to call it, in this direction. I can show it differently that too. So I can show it in 2D format. So here is the 2D format. Everybody see what I'm talking about? Yes? So this is, I try to show you here 3D. My picture is not that great. Everybody see that? Yes? All right, so here is your forces or stresses going out, correct? Yeah? But the thickness of that is the dx. Is that correct or not? Yes? Therefore, the forces going to, let's call it this direction, x. Doesn't matter what you call it, equal to 0. So from one side, I put it in red that you know what I'm talking about. Sigma 1 times the area. The area is dx times T times dx. Is that correct? But I have two of them, one on the bottom, one on the top, multiplied by 2, equal to forces going in. What's forces going in? Which forces do we have here? Those are as the result of this pressure, yes or no? Which is perpendicular to the surface. Everybody knows that pressure is perpendicular to the surface. So not all of them are horizontal. Everybody understand that. If I'm looking at this point, this force is horizontal. If I'm looking at this force, that force is in angle, so it has horizontal force and vertical. But in general, I have to calculate this surface, which as you see, it is that surface, curved surface, half of this circle, yes or no? This is the thickness of that, and I have to multiply it by P. P is not uniform, etc. But there is an approximation for that we did it in ME 218. Remember in ME 218 when we were talking about the pressure of a pin against we took the projection. We do the same thing here. So instead of putting this, we say this is equivalent to the amount of P going on the projection of this area, which is this height, and the thickness is dx. Is that correct or not? Yeah, remember we used that in ME 218. There is a 2-page formula. I can prove that that's almost the same. But you have to go through integration and all that. Is that correct or not? Which is not, again, part of this course. However, what I'm saying that instead of taking this P and multiplying that area, which is complex, requires integration, because here horizontal force is 0. As you see, the horizontal keep going, becoming larger, yes or no, because of the direction of the P. Is that correct or not? So instead of that, we take this one, which is like this. So we take this horizontal. This is what we take, this area. And that area is what? This is dx. And what is that? 2r. Is that correct or not? Therefore, that must be equal to dx times 2r inside, because that's inside the pipe, not outside of the pipe, multiplied by pressure P. Of course, this is plus and that is minus, but I put it equal to, this is equal to 0. You can write it like that. This minus that equal to 0. Yes or no? Forces going in, forces coming out. Correct? Did you get it? The only thing that some of you may be not getting at, instead of finding the pressure, is like that, guys. Instead, those of you who don't remember it, if this is like that, the pressure is like that. Yes or no? Instead of taking pressure like that, we take this part as uniform pressure over that part. This is approximately the same. Is that correct or not? It can be proven. It's not part. It takes about half an hour or 45 minutes to do that. But it is not necessary for you to know how, but there is an integration method for it. Is that correct or not? Because this is a curve and you see what the pressure. Is that correct or not? Yes, this is just, again, that's math. But don't accept that from me, that this is equivalent to that. Is that correct or not? But we get the answer here. Now, dx and dx drops out, yes or no? It's very simple. 2 and 2 and going to drop out. The sigma 1 become here. I'm going to put the answer here. At the result, sigma 1, which is along the circumference of the circle, inside and outside, they are here. See, if you have a point here or there, it's like that. Is that correct or not? Yes? So it becomes equal to, look at that. Sigma 1 become PRI divided by thickness of T. That's it. So that is, we call it circumferential or hoops stress, which is going around the cylinder. Yes.
Just to make sure this is only for thin wall pressure vessel, right?
That's only for thin wall. We cannot do it for thick wall. Thick wall, believe me, this equation to end up to be 3 line by itself. So, okay. I can show it to you if you come to my office. I have it. But it's really not necessary. This is for thin wall because, again, remember that what I'm saying, that the stress, when I do the example, I would explain this further. You will see what I'm talking about. The stresses inside is slightly larger than outside, because inside you have a sigma z coming. I'll explain that a little bit later on. This is only sigma 1. Is that correct or not? It is not along the length of the pipe, along the circumference of the pipe. Is that correct or not? This is because this is open-ended. Remember that case 1, so write it down. This was open-end pipe, or this is what I did here. Is that correct? However, as you have seen it at home, etc., you may have a tank, and a tank, what is going to happen? The tank, you are going to put a plate on the bottom of this pipe. Is that correct or not? So this is the same pipe, under the same pressure, except it is closed end. Is that correct or not? Like the picture I gave you. So the problem that we have, we call it pressure tank. So every time there is a tank full of gas, you have it at home, you see it to the factory, you see some of them. Is that correct or not? That is pressurized. Actually, your tire is pressurized system. Is that correct or not? And therefore, as you see, we have another stress. Now, what happened here? If I have here, you don't put a plate here. You don't. This plate actually heavily has to be supported. Why? Because the pressure tries to pulls that way. It wants to go that way, and you put here bolt or whatever you're welding. It has to withstand that stress. Is that correct or not? As soon, write it down. Case 2, close end. This was formula for case open end. But for close end, as a result of this pressure that applies to that plate, you are going to have also a stress in the x direction or along the axial pipe, and we call that sigma 2. Is that correct or not? Because the plate wants to move, pull the pipe with it. Is that because the pipe will be again in tension, of course. Is that correct or not? Yes? How much is that? Now we want to calculate that one. So for open end, we have only one sigma. For the closed end, now we have sigma 2. The question is how much is sigma 2 compared to the other one? And that's very simple, of course. To calculate that one, I'm going to do it under this scenario. This is the idea behind the thin wall. As long as this is applies, then it's considered thin wall, and those formula is applicable for design. Everybody understands. As soon as we become less than 10, then of course you cannot use this equation. Correct or not? Yeah. And by itself become a really difficult project. Now, looking at all I have to do now, as we do in a static class, all I have to do, look at equilibrium of this piece. Is that correct or not? Yes? Separate that piece from the rest of the body, which will be this. So that's the plate, and a little piece of pipe is there, an epsilon to the right of pipe, and that is the thing. How it looks like, actually it looks like that. Is that correct or not? Yes or no? Correct? Now, where are the pressures? The pressures, of course, apply to the plate. Yes or no? Correct? What are here? What are these? That is sigma 2. Is that correct or not? In tension. Because if you look at the other side of the pipe, I did not draw the other side of the pipe. So this is the other side of the pipe. So the other side of the pipe will be also in tension equal, and so that's what we are calculating, sigma 2. Is that correct or not? Yes? Pipe is under tension, correct? Okay, do this, so I know we need to get it. Yes?
Is the red sigma 1 or sigma
2? Now we are talking about sigma 2. Now we are talking about sigma 1 finish. I already finished sigma. Sigma 1 was along the circumference of the circle. That's it, finished. That was sigma 1, and that's the value of that, PRI divided by 2. Now I'm saying the pipe has a end. How do you end the pipe? You have to put a cap there, yes or no? You have to bolt it or weld it to the pipe, yes or no? If you do that, what's going to happen? Is the pressure is inside, yes or no? If there is no pressure inside, you don't worry about anything, yes or no? But if there is a pressure inside, what's going to happen? The pressure is going to apply to the plate. Plate wants to go that way. The pipe doesn't let it go, so the pipe become in tension. Yes or no? The question is how much tension? We are looking for sigma 2. That's the question we want to answer. Yes or no? In order to do that, I'm looking at this free body diagram. Yes or no? Okay, so how much pressure is going that way? So assume this is that cross section. Yeah. How much force these are the forces going in 3D, yes or no? And these are the forces coming or stresses coming out, yes or no? Coming up, all that way. All has to go the same way. Is that correct or not? Yes? Look at this one and that one, correct? So what's the black? How much black force? I don't have to show it like that. That you can do it yourself. You can imagine that's a plate, and inside of it is exposed to the pressure, yes or no? Correct? So how much is this area again? Is pi Ri square. Is that the amount of plate we have there? Yes or no? The cap without the thickness. Is that correct or not? Yes? There is a cap without the thickness. That's what you see. Is that correct or not? Yeah. And then times what? Times, what is this? This is pressure P. So assume this is going that way, which is negative, plus what? Sigma 2. Sigma 2 times what? Sigma 2 times the area. What area was that? Remember, that was that area. Yes or no? Correct? So it is actually area of outside minus area inside. But again, since the thickness is small, we can assume this is equal to 2 pi RO, which is this length, multiplied by, this is again approximate, multiplied by T. That's approximately the same thing. Yes or no? Correct? If you take this one and open it up, since the difference between these two are very small because the thickness is very small. Everybody understand? We are assuming the thickness is very small compared to the radius. Everybody see what I'm talking about? So therefore, you don't go that minus this. If you do that, you have to drop the t square out of the system because it becomes too small. Everybody understand? Then it becomes 2 pi rho times, as this is a band of like that, 2 pi rho, which is this circumference multiplied by t. Is that correct or not? Yes. Anyhow, so you get what it is. So multiplied by t. So that is this area multiplied by sigma 2, and that's what is coming out. This one is going in, and nevertheless, when you do that, you calculate the stress that you see here. One of this r and this r drops out, pi and pi drops out, and then as you see here, sigma 2 become equal to, again, p ri divided by 2t. It become only half of the other one. So
are you saying that Ri and Ro are the same?
what?
Are you saying R inside and R outside?
Oh, did I put r's outside? No, inside. I'm sorry. How can I drop? I said that was inside. I made by mistake. I put that. Therefore, sigma 2 become equal to p r inside divided. Actually, when you calculate one, the other one is half of it. As simple as you don't have to recalculate that. So one is, remember, sigma 1 always, the only thing you have to remember, sigma 1 is around the circular part. Sigma 2 is along the length of the pipe. That's the only thing that you have to remember. Is that correct or not? And I don't have to mention that. This is for cylindrical, for spherical, for a spherical sphere or spherical cylinder, sigma 1 become equal to sigma 2 become equal to p, because there is one example I gave you, Ri divided by 2t. So write it down that way without any proof, but you can prove that one as well. But it does not necessarily. So these are the equations given for cylindrical pressure vessels and a spherical pressure vessel. Any question? I said for cylindrical, sigma 1 become equal to sigma 2 because it is symmetrical. Everybody knows that. So if you have a spherical tank like that, like exactly like a basketball, everybody understand that, then there is at any point there is a sigma 1 and there is a sigma 2, and they are equal and they are principal stresses. There is no shear. Everybody understand what I'm saying? Yes?
Now, with the thick wall, obviously you're going to have to actually compute the area. Is there anything else that changes?
Yeah, a lot changes, yes. So the formula totally, you have to go to 3D stress analysis. All the undergraduate work is based on plane stress. Remember what plane stress was? It was the sigma z equal to 0. When I do the example, you will see what I'm talking about in a minute. You will see when you get the better understanding of that one. Total formula is totally different. It is a 3D stress analysis. It's just not that simple. Is that correct or not? By the way, this is what we are doing. For all the, sorry to say that, for all the civil engineering work, if you are designing a building, frame even a 20-story building or high-rise, still in this age, we are using the same old method of 2D analysis, because if you notice, we did all the beam and column with that one. But if you are going to machine design in future, and you are going to get into more sophisticated design, of course, you have to use the 3D analysis. 3D analysis is very complex. You have to go to lots of math before even you understand what we are talking about. The design, you go to the 3D analysis, and that's all graduate work. So some of you would decide to go graduate work. That's the way you want to do it. And by the way, if any of you decide to go graduate work before you go to any school, it's much cheaper here to get your master's degree in math here, because you have to know lots of math. You will see in this class, when we go to the beam next week, we are talking all about differential equation, guys. So all the engineering in future become differential equation as far as the stress is concerned. So you have to remember that. So you need to know lots of math. So take as much math as you want in this as your elective course if you are planning to go to master degree or PhD. Everybody understand that. That way you are ahead of this, getting your education ahead of going to any college. And many of us students, my past students, have done that. In fact, I have one student who got his master degree here and then get all the scholarship going to the school there, because he was very good and he just listen carefully and did exactly what I just told you guys to do, because this is the best way to get your get higher education if you want to. Anyhow, but some of you will decide to go to work, which is fine. Actually, he was working for a couple of years before he did that. Anyway, now let's go to that example. The first example, you see it in the handout. So let's look at all the aspects of that one. As I will explain that to you, you will get a better understanding of what you just said. The static of it is very simple. All I did, forces in and forces out. That was really not much to worry about it. The picture, you have to imagine how that looks like, but let's look at this tank, which looks something like that. So this is the tank I have given you to do. There is a cap there. So of course it is closed tank. Is that correct? It is cylindrical. Forget about where is it standing there, because we are not designing for that one. And let's look at all the data that is given. I need to get my example and take a look of all the information. First of all, it says internal diameter is given equal to 1.5 meters, correct or not? Yes? The thickness, look how small the thickness is compared. The thickness is 18 millimeter. The pressure inside is 1.2 megapascal. Yes or no? And all the question, I think I asked 4 questions or 5 questions, A, B, C, D, E. I have asked 5 questions there to be answered. Some of them is repeat, a few of them maybe is today's lecture. Yes or no? Correct? Now, it is very simple. The first, I asked you to find the state of stress on the outside surface of this pipe. Yes or no? Notice I'm saying on the outside. So you are on the outside. What stresses do I have? Now, don't look at the note. Don't look at that. Tell me which side is sigma 1, which side is sigma 2. That's your decision. You cannot make a mistake here. Where is sigma 1? Sigma 1 is not that way. Sigma 1 is here. Is that correct here? Because it was circumferential. It is around the circular shape of that. Yes or no? Sigma 2 is because the cap is here. See, this is reverse of what I just did a minute ago. Yes, sir. But that's a decision you have to make in every problem. So that is your sigma 2. So that's the state of stress on the pipe if there is nothing else happening. Is that correct or not? Yes? So that's a state of stress. I just gave you the formula. You just want to remember. You don't even have to remember. If there is a quiz or final, I'll put that on the board. But your decision to which side is sigma 1, which side is sigma 2, which is very simple. You already learned that. Is that? Let's calculate it. So sigma 1, this is part A of that problem. What's the state of stress on the outside surface of this pipe? So sigma 1 equal to P Ri divided by T. Is that correct or not? Which is equal to, what is the pressure? Now notice the pressure is a negative stress. Is that correct? It is, but the pipe is going to expand. So sigma 1 is in tension. So don't put a negative there. Everybody understand that. This is in tension. That's the magnitude. Is that correct or not? Yes? So therefore it is 1.2 times 10 to the power of 6 what? Pascal, which is Newton per meter square, multiplied by R. What is R equal to? Diameter is 1.5, so R inside is 0.750 meter or 750 millimeter. But we have to put meter there, so 0.750 meter. Is that correct or not? Divided by thickness, but thickness should be also in meter. So 0.018, if you multiply through, this becomes 50 megapascal. 50 times 10 to the power of 6. Would you please, guys, when you write to that number, don't write 50 plus 60 in front of it. So please. So we always talk about kilo and mega, everybody. And all the stresses, usually when it is like steel and aluminum and this sort of thing, they are all in the order of mega, 10 to the power of 6. Epsilon is in order of, as we saw it in previous quiz, at order of macro, which is 10 to the power of 1. And this is the typical thing you have to do in future. Is that correct or not? So good. Never use 10. Still, there are few students here, they are using this 50 times 10 to the power of 500, I don't know, 10 to the power of 4 or 5, 7, and 8. throw those out. You never write your answer in that format. Is that correct or not? Yes? Only 3, 6, -3, -6, or 9. Anyhow, sigma 2 is very simple. Sigma 2, I don't have even to calculate. That is equal to, because that one is also in the tension, but it's half of the other one, so it is 25 megapascal. Correct or not? Yes? So that's answer to question number 1. What's question number 2 or B?
Maximum shear stress.
The maximum, the absolute maximum shear stress. Yes or no? Isn't that what you were working here in this setup? Yes? Okay, what's that one? Part B. Absolute maximum shear stress at any point. First of all, this point doesn't matter where it is because, of course, we have a stress concentration there. Don't forget about that. Remember the stress concentration at the corner, but we are not talking about. We are assuming sigma is everywhere. Is that correct or not? Yes? Not true, but that's the assumption. Is that correct or not? Therefore, if I want to draw that, so notice that is already a principal stress. Yes or no? Sigma 1 and sigma 2 is very simple. So all you have to do, you put here your sigma, and you put here your tau with the arrow. Is that correct or not? What is sigma 1? Sigma 1, or what are the stresses going in this plane, again, in this plane, perpendicular to the x? Sigma 1 and 0, yes or no? So sigma 1, we come here at 0, so that's 50, correct? Megapascal. Of course, the answer. Now you go to the other side, put the stresses there. What the stresses there is 25 and 0, because there is no shear. Is that correct or not? Yes? So that is already a principal stress. So that is your in-plane circle, refers to what you learned here. Is that correct or not? Yeah. So if somebody asks you what is the maximum shear in plane, so you immediately answer tau max in plane, which is xy plane. Is that correct or not? Yes, this is x. Let's say assume this is x and assume this is y. Is that correct or not? Yes. So therefore, that will be how much? This is 50. This is 25. So what's the diameter is 25. What's the radius? Radius is 12.5. So you don't have to do anything. So that is 12.5 megapascal. But is this the maximum shear at that point? No. That's what you learned already. That's what your homework was about. You have to look at it on rotate. This is rotation about the z-axis. Do I want to rotation about y-axis, etc., etc.? Everybody understand what I'm saying? That yes. So therefore, what should I do? I should look at sigma z. What is sigma z outside of tank? Sigma z outside of tank is 0, because there is only air here. Is that correct or not? Therefore, this will be the third principal stress. Yes or no? Sigma principal 1, sigma principal 2. This is, by the way, x. This is, by the way, z, or you can call it ABC, whatever you want to call it. Remember, I call it different format because of different book. They call it principal 1, principal 2, and principal 3. Principal 3 is sigma z is equal to 0. Is that correct or not? So therefore, your other two circles become like that and like that. So which is the maximum shear here? First of all, it is the rotation about the y-axis. You saw it in one of the pictures I gave you, and that is the maximum of this. Is that correct or not? Which is tau max. This time, this is absolute maximum. This is in plane. This is absolute maximum. If that question comes out, which was in your homework, by the way. So, and that is in the xz plane, or zx plane, doesn't make any difference. And that is equal to 1/2 of, this is the way we wrote it, 1/2 of sigma max minus sigma minimum, but sigma max is 50, sigma minimum is not 25. Sigma minimum is 0, therefore it becomes obviously the radius of the larger circle, which is 25. You see that? Twice as much of the other one. This is what the extent of the book is. But now I ask you something else, which is really important. That's the question you were raising. If I want to do this inside the tank, what happens?
There's a sigma z.
What?
There's a sigma z.
There is a sigma z inside, isn't it? How much is sigma z inside? Pressure. Is it plus or minus?
Minus.
Minus, because it's negative, it's pressure. Therefore, if you are, it is not here, but well, let's do it. In case, that's what the difference is. That's what you were asking. There is a difference, a slight difference in inside and outside. But we are neglecting that. Remember that? Because we are saying the stress there is uniformly distributed. This should be larger, and that should be a little bit smaller, because there is sigma z inside and outside is not there. But since the thickness is too small to consider that, we are neglecting that. That's when if you want to go to 3D or thick wall, you have to consider that. So as you see, it's totally different stress analysis. Is that correct? Still is the same thing, but you have to go through integration and that's et cetera, et cetera. Yes?
So in this one, I'm guessing we ignored the atmospheric pressure, so we can do it again.
Yes, you can answer that. That's good enough. Yes, but I'm doing it for you to see what happened. That if that was the case, let's put here. Just let's put it that this is for inside. Oh, outside. I'm sorry. This is for outside. If somebody asks you what is inside, and the inside, which is stresses, is larger, therefore, look what happened. Then on the inside, look what happened. Here you have 50, one of the principal stresses. Then you have 25. Then you have here minus P, whatever that is, which is 1.2, which is very small, as you see that. But nevertheless, these are your three circles. This is original circle. This is out of plane circle. As you see, it is stress is a little bit larger. Now, if it is too thin, let's forget about it. If it is thick, that's a different story. Remember that this formula doesn't work. Then there are a larger difference between outside and inside, so you have to design it. By the way, this gives you a good indication. This is the only time that I forgot to mention it in the other class. This is the only time that the object is going to break from inside, not outside. That's why if you take your tire next time if you have a flat, take it a tire, and the guys put his hand inside the tire and say, change the tire, don't get mad at him. Don't think that he wants to get your money. If there is a sliced abnormality inside the smallest crack there, that's the danger. It's going to blow out pretty soon. So it is worth it to change the tire. Everybody understands. But the guy doesn't know that. Every time you go there, I don't know whether you have noticed. He puts his hand inside and goes like this. Have you seen that? To see whether there are any damage. Because the pressure vessel break from inside. Because we are assuming the stress inside and outside is not equal, but actually inside is much more. Is that correct? Everybody understand what I'm saying? So you have to be very careful. On the pipe and the plane, when it's on the ground, on the beam, on the column, maximum stresses are on the outside. Remember, sigma was MC over I. We never went inside the beam. Is that correct or not? Or TC over J, which is outside. Correct? All of that part of it here. Anyhow, that's problem number 2. So actually, as you see here, tau max actually become 1/2 of sigma max, which is 50, minus 1.2. As I said, it's very small. So it become equal to 25.6. As you see, it's a very small portion of that. It's very small to consider, especially if you are using a factor of safety of 2 or 2.5. Who cares about that? Is that correct? But if the suddenly 25 become 30 or 35, that becomes the thick wall. Okay, question number 3. What's question number 3, guys? So question number 3, because I'm doing that, prepare you for everything. So question number 3 is calculating there is cap. So the cap, it says, the way it says it, the cap are bolted. Yes or no? Yes? So let's erase that. Right. We need a couple of more new erasers. Okay, so this is the cap, and there is, I believe it says there is, how many bolt is there? 16 bolt. Yes or no? Is that correct or not? Yes? What is the force in the bolt? Are the bolt under tension or compression? Tension. The cap wants to go up and you're bringing it down, so it is under tension, correct? So the question is, what's the force in order to design those bolts? Of course, the force will be going like that. Is that correct or not? Yes? We already did that, correct? So all you have to do, write forces going in and out, or you can look at it sideways, top way, or whatever you want. So here it is, and here is at the pressure is circular shape, so it's P times pi R inside the square, which I did it in one of my analysis. Is that correct or not? Yes? That's for the forces going up. Yes or no? But what is these forces will be taken there by forces going in the bolt. Is that correct? Because the bolt is going to be in tension. This is like how it's going to be. Is that correct or not? Yes. So therefore, so it's going to be equal to 16, and we have force. Let's put the force in each bolt. Because there are 16 of them to resist that force. So therefore, you can call this plus, that minus, or vice versa, doesn't matter. But what is important, this is equal to that. Or force in each bolt equal to look what the number becomes. Pressure, which is 1.2 times 10 to the power of 6, times pi, which is 3.14, times R inside, which is 0.75 to the power of 2, divided by 16, because we have put 16 volt there. Yes or no? And when you calculate that one, that becomes 133 kilonewton, or 133,000 newton. Look how important this bolt is. And many times, if they are weak or they become rusty or something, because the head is going to explode. And you have seen a lot of that happening. I'm living next to the Torrance refinery. Every month or so, something goes wrong with that, because the old refinery, and anytime actually they have twice or three times they had explosion there because of that, because there are all pressurized gas inside every pipe. Everybody understand that. It's very, very dangerous situation. You have to design all of that, correct? So now let's go to part D. See what you remember from ME 218. I throw that in last night for you to see, or the other time when I prepared that for Tuesday class. What is change in diameter? So where is the diameter? This is the diameter of the tank. Let's look at outside, not inside. Correct or not? Okay. What's the diameter of the tank outside first? It's not equal to inside, yes? It's slightly different, correct? So what is the diameter of, there is diameter outside is equal to 150 or 1500, it was 1500 millimeter, correct? Plus 18 and plus 18, correct or not? 118 on both sides, yes or no, correct? So that is equal to 1536 millimeter. So as you appreciate, when this expands, like your basketball, if you put more air to it, this is going to get larger. Is that correct or not? So this area here getting larger because diameter is getting larger. So what do I need? How do I calculate that? How do I calculate the change in the length? What do I need? What? Epsilon, very good. In which direction? Look at it. Epsilon in x direction, yes or no? So you need epsilon x, and epsilon x equal to what? This is again, because I recalled a week ago somebody in this class asked me, we reviewed everything except the epsilon and Poisson ratio. I don't know who it was, but I remember I said, okay, let's practice it. Okay, epsilon x equal to what? Sigma x over E minus nu sigma over E minus nu z over E. Every one of you are familiar with this one? In ME 218, you should have covered the 3D format of it, not only uniaxial. This is triaxial, because you may have sigma x, you may have sigma y, and you may have sigma z. Is that correct or not? It's very simple, but I'm just reminding you that. Then, of course, there is an epsilon y, and there is an epsilon z. Let's write it down, those as well. So that's minus nu sigma x over E plus sigma y over E, because sigma y is the actual force or a stress, and minus nu sigma z over E. And finally, epsilon z become minus nu sigma x over E minus nu sigma y over E and plus sigma z over. Notice this and that are the actual stress, and the other one are the result of Poisson ratio. Is that correct or not? Now I need epsilon x. So epsilon x, of course, in this problem, on the outside of the tank, again, sigma z equal to 0. That's the whole idea here. So you have not 3D problem. Actually, you have a 2D. So it's only epsilon x and epsilon y. Epsilon x equal to 50 I'm sorry, sigma x equal to 50, sigma y equal to 25. Is that correct or not? So all you have to do, put their numbers there. Notice I have given you the nu and the e. Is that correct or not? Yes, look at the handout. Yes? Okay, so therefore it becomes equal to sigma x, which is 50 megapascal times 10 to the power of 6, divided by modulus elasticity, which is 200 times 10 to the power of 9, minus 0.3. I believe I gave you 0.3. Is that correct? Yes, times sigma y, which is sigma 2 in this case, 25 times 10 to the power of 6, divided by 200 times. So it becomes equal to, actually when you solve it correctly, it becomes equal to 250 micro. What's micro again? 10 to the power of minus 6. You don't need to put too many zeros there because that's confusing. And minus this one, when you calculate that one, that becomes equal to 37.5 micro. Micro again. Yeah. So the total will be 212.5 micro. And then if you want to calculate delta of, let's put it this way, delta of change, change in the diameter d, as we call it delta. So of course, this is the amount of change per unit of length. Is that correct? Or that's the definition of epsilon? Yes or no? So therefore, it becomes 212.5 times 10 to the power of minus 6. That's the amount of change per 1 millimeter. How many millimeter do we have there? 1,536. By the way, when I calculate the change in the diameter, I can calculate the change of this circumferences as well. Everybody understand? That's what is changing, actually. Is that everybody see what I'm talking about? That's why we need epsilon 1. Is that correct or not? Yes? But we do it this way, but that's the same thing because the same proportion. All I have to do multiply it by pi. Is that correct or not? Pi times diameter. Everybody see what I'm talking about? Therefore, that diameter changes. What was the diameter? It was 1,536. Don't calculate that in meter or in mile, please. Calculate that in millimeter because it's so small. Everybody understand that. So therefore, it becomes equal to 0.326 millimeter. Notice I changed that from meter to millimeter. Everywhere else we are using meter, but here we have to use millimeter, or for our system use inch. Is that correct? The minimum that we have. Correct? Can you change in the thickness of the cylinder? What's the question? Is there any question?
Yeah. What was mu in the problem before it got so weird?
New?
Yeah.
Given 0.3 as Poisson ratio. It was given in the problem. Do you have a copy of the problem?
No, I don't.
So that's the problem. It's there. It's given. I gave it to you. Nu and E is given to you. You have to. That's property of material. Different material, different Poisson. But what is important, that's lateral strain versus axial strain. That's the definition of it. Yes?
Is that for the inner diameter or outer diameter?
What diameter?
The change in diameter.
That's the change in diameter. That's right. That's why I said delta D. So diameter, which was 100, is become a little bit bigger. As you see, it's expand. Yes or no? But you see the expansion in the balloon by eye because that doesn't follow the elastic rate. But you don't see a structure in the pipe. Is that correct? Because it's not visible by eye. Look how small it is. But anytime it is empty or if you put pressure, it is going to expand a little bit. Yes or no? And that's so minute. It's not like the beam. We see it next week. This beam is going to deflect, but you don't see it, do you? Column is when it's loaded. When you go in the room, all the column gets a little shorter, but they are not going down 1 meter. Is that correct? No, that's not. That's absolutely very small quantity. But they are all under deformation. When you load something, it goes through the formation. That's exactly like that. Yes. You have lots of work to do. Go ahead.
Yeah. For our sigmas, they're they're correct, or I guess they apply for both the inside and the outside of the vessel.
We are assuming we are
As far as
neglecting
the
the
skin,
inside,
yeah.
remember that.
So then for this, for when it asks for the change in the thickness of the tank, would we just do the same thing but just multiply it?
I mean, if there was sigma z both sides and you want to consider from inside and outside the sigma z, then you put the sigma z in the formula. That's it. That's the difference between not having sigma z or having outside. We don't have inside. We do, but we are neglecting that. Remember that? Because that was the idea behind the thin wall pressure vessel, which I mentioned at the beginning. We are assuming the stress inside and outside are, notice, the radius is large, the thickness is too small to consider. Everybody understand what I'm saying? That
So I guess
if
the question is just
if the pipe is 4-inch pipe and there is a 4-inch thickness, which is that's totally different type of stress.
okay,
Yeah.
so since we're neglecting this, we could reuse that epsilon x, right?
Yes,
Okay.
that's right. Exactly. You calculate epsilon inside, probably you have to put sigma z there, but that's 1.2 divided that, which is really become too small to consider. We are neglecting that. Yes.
Did you explain why we can use epsilon or EZ?
Easy. Epsilon.
That third equation. Like why we
There is no sigma z from outside of the tank. Is there anything, if you have here, put water in it. Actually, one of your homework is like that, by the way. The water inside. Is there anything coming here?
No.
That's it. So sigma z equal to?
0.
That's what we are talking about. But inside there is a little pressure. That sigma is z direction, yes or no? That's what he is saying, that inside I should consider that, yes or no?
Yeah.
But I said it's so small compared to the other because it's too thick and pressure is so small, we are neglecting that. Look, 1 megapascal versus 50 megapascal. Do you see that? That in this theory, that's being neglected. That's what we are saying. However, as you can appreciate, there is a difference than inside that, outside, yes or no? And if it become a thick wall vessel, so you have a vessel like this, obviously you cannot use theory because the stresses here is going to be much larger than that. Everybody understand? Actually, we have to give you here a distribution of a stress, how this works. Is that correct or not? Whatever that is that correct? Or that's what we are discussing, actually. But this one, look how large it is. This is 1,500 millimeter versus 18. We are neglecting that. That's why we are calculating. Remember when I was driving that, I was putting the stress uniformly distributed from outside to inside. I call it all sigma 1. Did you see that? Yes, that was the idea. Okay, let's go to last problem. Can you calculate the change in the thickness of this? Yeah. Yes? What should I calculate? Do I need epsilon y or do I need epsilon z? Epsilon z. Everybody understand that. If I want epsilon y will be the change in this direction. There is that one too. Everybody understand that? Yes? Epsilon z is change in the thickness of that. Can I calculate that? So how do I calculate epsilon z? This is epsilon z. Is that correct or not? Again, this one is, we are out on the outside of the pipe. We are assuming that one is 0, yes or no? Correct? So we are using minus nu sigma x over nu minus, of course, if you stretch something this way, thickness becomes smaller, yes or no? If you stretch it this way, thickness becomes smaller. So you get negative and negative. So that formula shows you. These are all in the book. You have studied ME 218, and we need that in 2-3 weeks, 3 or 4 weeks. We are going to spend a week talking about this. Stresses, normal stresses, shear stresses, and the relationship. There is a lot more circle about this. We have to draw more circle for this. We have lots of work to do. Indeed, that's why you need to go back again, study this. Is that correct or not? That's this chapter 2 or chapter 1 of your book. Anyhow, epsilon z is equal to epsilon z, we already calculate that, minus nu sigma, in this case, sigma 1 over E minus nu sigma 2 over E, which is sigma x or sigma y, doesn't matter. That you just put there. So we had that minus 0.3 times, how much was it, 250? And then the other one was minus 37.5. We already calculate that part because from the previous equation. So you put 2 and 2 together, so it becomes equal to minus 75. That becomes 37.5, so it becomes minus 75 micro, and then if you want to calculate the change in the thickness, you say minus 75 micro multiplied by the thickness, which was 18, which is very small quantity. Is that 18 millimeter was nothing, so that one would be much less than 1 millimeter. Is that correct or not? Yes? Very small quantity. But however, gives you the idea how these things work. Is that correct or not? Okay, I have about 5 minutes to discuss something which is very important, which takes, I was hoping, guys, that to be able to finish the beam design, and then hopefully on Tuesday to do the shaft design, because shaft design is a little bit more expensive. Now let's go to the beam design and at least give you a little bit of what's happening in the beam. Actually, the subject is principal stresses in the beam. And what that comes to is this guy. So if you have here a beam like this, and you put a simple load here, P only, nothing else, and this length is L, a lot of things happening in any cross-section here. This cross-section, first of all, will be different from that cross-section, will be different in as far as the stress is concerned. Yes or no? Because as you go further, the amount of moment changes. Yes or no? And since this is going to be under bending, look what happened there. If I draw that free body diagram at a certain distance A, not L. So let's say L is 10 meter, and now I'm at distance of 8 meter. So if I'm there, of course, everybody can see that internally you have here a shear going upward because this is going downward, yes or no? And there is an action here, so you have a moment there. Is that correct or not? Tension on the top, compression on the bottom. The question that you want to answer for next time by yourself, if you want to go ahead and read the handout that I gave you, which is very handy. Actually, it is review. You should be able to put it together, but I give you some hint. Are the stresses here and here and here and here the same or different? Obviously different. But look what happened on top. If I'm looking at this point, at that point on top, or this point on the bottom, I'm going to repeat that next time after that. Do I have normal stress there? Yes or no? Here I have a normal stress, sigma equal to what? MC over I. On the bottom, what do I have? Normal stress of MC over I. On the middle part, let's forget about the other two parts. The middle part, I do not have anything. Yes or no? But when it comes to the shear stress, then what's going to happen? On the top, there is no shear. On the bottom, there is no shear. Where is the shear maximum? Depends on the shape of it. Is that correct? So let's assume this is a rectangular cross-section. Yes or no? For rectangular cross-section, where is shear stress is maximum? This tau was equal to VQ over IT. Correct? Chapter 6. Actually, a couple of people in this class or the other class ignore that. Whenever they're calculating the tau, they put force over area. That means you have never heard about chapter 6, ME 218. Is that correct or not? Yes? So if you have a shear force here going like that, so stresses here is what? Shear stresses I'm talking about here is 0. Shear stress here is 0, and the format of a stress distribution is a parabola. Yes. Where is maximum? On the neutral axis. Yes. So let's calculate that, because that's what I did that for the other class, because one of you had asked you. Tau max. This is only for rectangular cross section. Don't get it a rectangular cross section. Only for this problem, not any other problem. Let's consider this as B, and let's consider the height as h, as usual. So tau max will be on the neutral axis because T is constant. Everybody understands. If T is constant, I is constant, shear force is constant, the only variable is Q. Tau max on the neutral axis will be equal to shear force, I cannot do anything about it, divided by I. What's I? 1/12 of, because this is rectangular shape, 1/12 of B times h cubic, correct? Multiplied by T. What's T? T is the thickness here, which is B. Very good. And what is Q? Q of that area with respect to neutral axis, which is H over 2 times B. Is that correct or not? H over 2 times B times what? Times this distance, which is H over 4. Correct. But if you put all of them together, this becomes, somebody again asked me, what is this equation? That becomes for rectangular shape only. You don't have to worry about this anymore. From now on, you can use this formula, which is much simpler. That's the tau max in a rectangular cross section. And that's what you saw some people using in the solution manual. Have you seen that before? Okay. So there is more stuff coming because I can do the same thing for the wide flange beam, because wide flange beams also have a formula, simpler formula than VQ over. Then we go to the design. It takes another 10, 15 minutes. So